In this video, I'd like to discuss something called the velocity-dependent force. So imagine the following scenario. We have an object, and it's traveling through air. Let's imagine that this is a ball that's traveling through air. It's traveling with a velocity v. Now, if the velocity of the object, the speed of the object, is 0, I don't expect that the air will offer any resistance to the motion of that object. So imagine that this object is going in a straight line through the air, and we're only going to be looking at the forces acting on the object horizontally. So if this object, right, is traveling with velocity v, let's say it's traveling at 10 meters per second, the force of the air is going to be backwards, so we're expecting a reaction force, a frictional force, some kind of a force that's acting backwards. So we expect that this force, right, this reaction force of the air, so I'll call this air force, that's based on the velocity, right, is basically a function of the velocity, because when v is equal to 0, we don't expect that this force to exist. But as v becomes more positive and starts moving, we're expecting a force of the air resistance pushing you backwards. So as I go forward, there's air pushing on me, in this case the ball. I expect that this ball, right, we can imagine that this force, right, is something called analytic. It could be an analytic function. And if this analytic function, right, if it's an analytic function, we expect that when somebody says sine, it's an analytic function. We're expecting that this is some function of polynomial. It is a polynomial in the variable v. So we can construct a polynomial, an infinite polynomial, that looks like this, where these numbers, right, are replaced by measured values. So we could actually measure different values of the force pushing on an object as the object's velocity is increasing. And we could eventually measure all these values of A0, A1, A2, and A3. But I know that the force of the air acting on this ball must be at 0 is equal to 0. And if it's equal to 0, then I can say that A to 0 is 0. Because there can't be a force acting unless the air is pushing on me and there's a wind pushing on me. If I'm not moving relative to the air, there should be no air force acting on me. So I can estimate that A0 must be 0. So now we reduce this analytic function to this analytic function is a polynomial, and now reduced into this. Now A1, right? Now, if v is very, very small, so this is approaching 0, meaning it's not 0, but it's approaching 0. Remember what this means. Whenever we do this in calculus, right, v is approaching 0, but not 0. It's very small. If this is very small, then v squared is much smaller. For example, if v is 10 to the minus 10, v squared is of the order 10 to the minus 20. V cubed is 10 to the minus 30. These orders, right, are very small. As v is very small, so how small? Well, a small number. This small v squared is much smaller, v cubed is much smaller than that. So to a first order approximation, right, for small velocities, I can estimate that, this is a guess, that the force of air is equal to some constant times the velocity. So this is our first order approximation. Approximation for air resistance. Now let's be more specific. I also will assume that if the ball is traveling to the right, then it experiences force backwards. But if the ball is traveling with the velocity in the opposite direction, right, so it means that if the force minus v must be equal to minus A1v. So the negative force is acting in the opposite direction. Now because it's minus v, actually, hold on a sec. So this is minus A1v. I want to make sure that A1 is positive, and to do this, right, I'm always put a minus in front of this symbol. So in this case, I could treat A1 as positive. if A1 is positive, right, then our first order approximation for air resistance is some positive quantity that has this, and so the 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 air resistance F air times V is some positive quantity, I'll call it A, times the velocity. So this is a first order approximation for air resistance if V is very, very small. Of course, so there's higher order terms, and I can use something called isotropic propagation to show you that the V squared, V to the fourth, V to the sixth term should all be zero, and that the next order approximation, if isotropic propagation, meaning that if I'm traveling in that direction, the force that the air resistance should be exactly the same as traveling in that direction, but in the opposite sense. And I can show you that the higher order terms, right, must be of the form of V to the 3, V to the 5, V to the 7, and so on. But, you know, we're only going to solve this because this is what I really need for air resistance. So let's go to a model of an object being dropped from, so this model, right, of the first order velocity dependent air resistance or liquid resistance, right, we can apply it also to the motion of a ball traveling in water, for example, or some kind of an object like a submarine traveling in water. So for example, here is some liquid, here's our submarine, here is the propeller, it's traveling with a velocity v, and to a first order approximation, right, I can assume that the force of resistance, let's call it Fr, to water, R, is equal to some constant b, the negative some constant with the velocity v. So we can get this, of course this b, right, will be dependent on the shape of the submarine, the, well, something relating to the water itself, but this constant is different for different objects and different liquids. Also, if this is an air, right, we're expecting a constant that's also dependent on the shape of the object and the air type of air. So for example, if you have a humid air, right, we'd expect that there's more. So if it's like a cloud, you're in the middle of a cloud in the atmosphere, right, I expect that this resistance A is very large. If it's like pure, there is no clouds and a clear, warm day, then this, at high temperature, we expect A to be much smaller. Lower temperature, you expect A to be more resistant, so A is larger. But the main idea we want to look at is a velocity-dependent force. So I'm going to assume that we have an air resistance that's proportional to velocity. So imagine the following example. So this is an example of using the velocity-dependent force. So imagine that an object is dropped from an, I don't know, some high place, okay, a mountain or something. Let's make it a high place. So here it is. So here's the object. I hold it and I drop it. Now, usually, right, we expect that if we did a free body diagram on the object, right, we'd say, well, there's force of gravity pulling down. So here's our free body diagram. This is force of gravity pulling down. And then there's a force of the air, right, force of the resistance to R that's acting up, because as the object is coming down, force of resistance is pulling down. If we didn't have this force, right, and we're in vacuum, you know that the sum of all forces using Newton's second law is equal to the force of gravity pulling down, and if there is no air resistance, we'll just get mass times acceleration. And we know that acceleration is due to gravity, and so we can estimate exactly the motion. But what exactly happens, right, if there is force of air resistance? So let me remove this and write this in terms of there is now a resistance that's a velocity-dependent potential, and that's equal to mass times acceleration. So this is the case where you have gravity pulling down, but as the object is moving faster, there is a higher air resistance acting up. So gravity is pulling down, but as the object falls, it hits more and more air, and as it hits more air, it's getting pushed back up, so there's an air resistance. And my first order model, right, for saying this, right, is that the force of friction is equal to the negative of some constant. Let's call this the value b, and with the velocity vector v. Force of gravity is nothing more than Fg is equal to mass times g, and I'm going to assume that down, actually let's put up as positive, which is j, and down is negative, so this is actually minus j hat. So let's plug this into this equation. In fact, you know what, I'm just going to assume one dimension anyway, so let's call it minus mg down. And so we get an equation that looks like mass times acceleration is, so if I assume up is positive, x, actually maybe use y, okay, because I don't want you to get confused with direction. So I can write this equation, right, as sum of all forces acting on mass times acceleration, which is d squared of dt squared, is equal to the force of gravity acting down. So this force of gravity is basically minus mg, but the force of air resistance is minus bv. So what is velocity? And I should write down velocity. It's dy dt. So this is the differential equation I'd like to solve. And I'd like to explain the idea of something called, well, when you drop an object, right, eventually it reaches the velocity, right, the force of the air resistance will balance the force of gravity, and then the acceleration of the object becomes zero because it starts accelerating faster, but the air resistance backwards, right, the upward force is going to be pushing on it. At a certain point, this force of resistance of the air and force of gravity, they'll balance each other in opposite directions, and the acceleration of the object is now zero. And if the object's acceleration is zero, it's going at a constant velocity. We call that terminal velocity. So I'd like to get an equation that relates the value of b to the terminal velocity. So the terminal velocity, so for example, a parachute guy, if somebody jumps out of a plane, he's accelerating towards the earth, but then the air resistance of the air pushing against his body, right, pushes him up, and that'll balance the force of gravity, in which case he's now going at a constant velocity down. That's called terminal velocity, and I'll actually call this Vt, okay, Vt for terminal velocity, Vt. So this is the equation I'd like to solve. Now, so let me erase everything and spend some time explaining how to solve this. And the reason I'm talking about this velocity-dependent potential, right, is that the general form of the equations that we'll be talking for energy dissipation, this term, right, is actually gives something called an energy dissipation. This term, this value, this component, right, gives you some energy dissipation. It's caused by this one term. If we didn't have this, right, then we wouldn't have to worry about doing these calculations in terms of Newtonian mechanics. We can do the whole thing in terms of something called Lagrange equations of motion. But when you have a system with energy dissipation, or in this case, this energy dissipation comes in the form of a velocity-dependent force. The simplest happening be b times velocity. So I'm going to try to solve this equation. So I'm going to rewrite this equation right over here. So here is dy dt squared mass plus b, I moved everything to one side, here's dt plus, actually I'll leave the mg on the other side. If you're looking at this equation, right, you should think of it, oh look, this equation reminds you of this is an example of a linear differential equation. It's inhomogeneous, but it's got constant coefficients, and we know how to solve it. Okay, so we could use the ideas of linear differential equations with constant coefficients and solve for y, but I won't do that. I'll actually use a simpler technique for solving for, I don't care about y, I actually care about the velocity. So I'm going to rewrite this in a different way. So I'm going to say velocity, right, is dy dt. So again, we can solve this, right, in using um, linear differential equation with constant coefficients, and this is an example of an inhomogeneous version, but I don't want to. Instead, I really want to solve this in terms of velocities because I want to relate the value of b with the terminal velocity. And also, I want to see a general form of second-order differential equation that you're going to see a lot when you do well, analytic mechanics or classical mechanics. So I'm going to rewrite this equation. I'm going to say I'm going to divide by m, so let me divide by m first. Here is b over m is equal to minus g. Okay, sorry. dy dt minus g. And I'm also going to say that velocity is dy dt, so we'll get a first order differential equation. dv dt plus, and b over m, I'm going to give this a notation of gamma. We're going to see this. So the reason I'm actually doing it this way, right, is that earlier, right, you might have already seen a video, right, that I discussed a spring mass system with no dissipation, a non-dissipative spring mass system. And so that equation, right, basically had d squared x dt squared plus, and some other terms, but I wrote down omega squared x is equal to 0. I'm going to look at this, and so this is for a non-dissipative spring mass system, and so you had vibrations in the system. Eventually, right, we're going to get to a differential equation that looks like this. I'm going to say there's something called a gamma, which is like here, like gamma over here, so I'll put the gamma over here so you can see it better. So this is this differential equation that I like to spend some time at. So we'll get several of these equations that are basically, they all look the same. You'll have some kind of set of symbols in front of the first order derivative. Then the second order derivative is 1, and omega O squared is actually in terms of the x. And so this is a homogeneous equation. It's a very important equation, and I'll be discussing it in another video explaining critical damping, underdamping, and overdamping. So whenever you get an equation like this, right? So this equation is a special case when gamma is equal to 0. And this equation right here is a special case when omega squared is 0. So they're quite opposite to each other, but generally these equations, right, we're leading into this one equation. And eventually I'm going to even modify this with an example of something called driven oscillation, where I'm going to force the system to be driven by some oscillation, and it will look like a sine of omega t. This omega and omega O are different. So I'm driving the system, and the question is, what is the response of the system when I drive this system? So this is the general equation that you need to solve for analytic mechanics, and it has to do with driven motion and oscillation. Okay, so anyway, not in this, so if you're wondering why I'm using gamma, I'm using it because I know we'll be using it later, and I'll be relating the mass spring system on a frictionless surface, that type of oscillation, with a dissipative system and putting it together. So I'll have a mass spring system with dissipation, and that dissipation is in the form of a velocity-dependent dissipation, which is exactly what v is. So this is the equation I'd like to solve. So let me erase this, and let me write this down as gamma is equal to v over v. And we can solve this using the idea of linear homogeneous equation with constant coefficient, and do the homogeneous and inhomogeneous, but I won't do it that way. This equation is simple because we can actually solve it using simple separation of variables. So taking this equation, I can multiply by dt. I'll move everything to one side. I'll actually move everything to one side, so I'll get dv, and so this is plus gamma v plus g dt. So I did a separation of variables. Well, I didn't finish yet, so I'll divide by gamma v plus g on both sides, and so you're left with dv over gamma v plus g plus dt is equal to 0. So it's a dv over gamma v plus g plus dt is equal to 0. And this marker is dying on me, so hold on a sec. So now I'm going to multiply this by an integral operator. So I'll multiply this by t is equal to 0 to t on both sides. So I'm going to multiply this. And so what we get is, so let me erase this on top. I don't think I really need this. Just remember b over m is gamma. So here is our integral. T is equal to 0 to t of dv over gamma v plus g plus the integral of t is equal to 0 to t dt. And this is 0, so you can consider this 0 dt if you feel like it, but whatever, the answer is 0. The integral of 0 dt is still 0. And so we're left with, so I'm going to multiply, I'm going to write this again. I'm doing these steps because you might not have seen it in this way. Gamma v plus g all over gamma v plus g. The differential of gamma v plus g is gamma dv, so I'm going to divide by 1 over gamma. And the integral of this is actually just t. It's t limited from t equal to 0, so that's just t. And so now we have, I can multiply through by gamma, and then evaluate this. So this is actually the logarithm of gamma at v plus g taken from t is equal to 0 to t, which is equal to minus gamma t. You're taking the limits. I'll call v at 0, the time at 0, I'll call it v0, and vt, I'll just call it v, so I don't have to waste time thinking about what the v is a function of time. That's the assumption. So erase this, and so take the logarithm of these two sides. So now we get the logarithm. The logarithm of the difference is the components divided by each other. So this is gamma v plus g all over gamma v0 plus g is equal to minus gamma t. Taking the exponentials on both sides, we're left with gamma v plus g is equal to gamma v0 plus g acting on e to the minus gamma t. And so I can keep going and solve for v. So v is equal to gamma v0 plus g e to the minus gamma t minus g all divisible by 1 over gamma. 1 over gamma. So as time progresses, right, as t gets larger and larger, this term becomes 0, and you reach a terminal velocity. So as t approaches infinity, I'll put this as an arrow, t approaches infinity, vt, or I'll just abbreviate it as t gets larger and larger, this term, right, drops out, and you're left with that the terminal velocity, this is what we call as the terminal velocity, is going to be equal to minus g over gamma. And if you look at what gamma is, right, that's minus g over b over m, which is equal to minus mg over b. So this is all completely separation of variables. So So we now know that if somebody knows what the terminal velocity is for an object, I should be able to calculate B. So solving for B, so minus mg over B is the terminal velocity of the object. So this is so if you drop a ball or somebody's a parachutist and is dropping, so our first order approximation was that there is air resistance based on the velocity only. And if we solve for B, B is equal to the negative of the weight of the object divisible by the terminal velocity is equal to B. So we can actually measure, so all we have to do is drop an object. So for example, if I'd like to calculate B, for example, some object falling in water, I can take a large graduated cylinder. Here's my, well, that's not a very good graduated cylinder. So imagine that I'd like to measure an object and I'd like to know something about the resistance of the object in liquid. So here's a ball, and I can assume that the ball reaches terminal velocity very quickly. It falls through the water, it's falling through, and then it's accelerating, but then at a certain point it starts going at constant speed. So imagine this is a very tall cylinder, and I measure how fast it's traveling in this time, so I can get the terminal velocity, assuming that it reaches terminal velocity very quickly and it's now going at a constant speed. I can calculate the terminal velocity. I know that what the mass of the object is. I know G is 9.8 meters per second squared, the mass of the object. I can calculate what B is. And if that's true, I can calculate the general rule that says that the resistance R is some constant times B times V. Anyway, the point of this is that this type of system, right, where it's a velocity-dependent force, right, will actually lead to dissipation. And that dissipation is a term that we're going to see generally in many systems. In many systems that are, for example, oscillating, an oscillator, there will be some energy dissipating out and it will be proportional to the velocity. So we'll see this time equation. All this is showing that all this is leading to a general equation of looking at a second order differential equation that looks like this. Gamma dx dt, oops, that's a mistake, plus omega O squared x equals 0. And then we'll extend this further, right, by changing the 0 into some kind of a driven motion, and then we'll talk about how what happens to a system when it's being oscillated, it's being driven. So for example, I have a swing. What exactly happens when I push the swing at a certain rate? Now if I let the swing go, if I'm pushing somebody on a swing, it naturally goes at a certain frequency. That certain frequency is actually related to omega O. But with dissipation, right, air resistance and stuff, right, that oscillation, right, is slowly dying down. So this is called underdamping. So I'll be discussing underdamping, overdamping, critical damping, and how it relates to me pushing on the object, that's called driven motion, and how I can get, for example, resonance. At a certain frequency of pushing, right, the system actually undergoes larger and larger oscillations, pushing on the swing. And all these are based on this equation. So all this, right, is not just independent. They're all coming into this one equation. So when gamma is equal to 0, then we have the simple system, oscillatory system with no dissipation. And when omega 0 is equal to 0, right, then we just have a pure dissipative system. And if this is not 0 and you have some kind of a sinusoidal function, you're having a system that's being driven periodically. So all this is coming from this one equation with like changes. So the reason we're doing this problem, right, is that you can actually see this as one equation, but we're solving it separately. So anyway, basically, so this is a special case of a dissipative system where the force is dependent on a velocity, linear velocity.